All right. Good evening, Miss Emily. I got my writing pad up here. I got your problems. Over here, we'll start with the easy one first, the box beam. So let's just get over to the writing pad and we'll get into it. By the way, hope you're having a nice summer. Not just doing engineering, but other fun stuff. Okay. So here we go with this particular problem. I think most of what you have is quite good. So we've got this box beam. We're looking or interested in section NN. Okay, that's all fine. First thing you need to know is what is the transverse shear at this particular location, this location NN. And I think you kind of rightfully have this sort of figured out, where if you have this particular beam and you got these loads, here's P, then the free body diagram is going to give you this and this, which is also P and also P, since we have this like symmetric situation. And if you're interested in like this portion of the cross section and you think about your shear diagram generally, then it's going to look like this. And these values are the value P. So this is P here. So the shear that is at that location, cross-section NN, is the value P. So that is 12 kips. So that's good. I think the more concerning part about like what I see in your work is your area moment inertia calculation. And I understand your area moment of inertia calculation here is like pretty accurate, but you don't need to split it up into like the various portions. I think it's a lot easier to think about this particular cross section here. You just have like 4x4 on the outside, and you have 3x3 on the inside. Okay, so this is 4" by 4", and you have 3x3. So one quick way to calculate area moment of inertia here is just 1/12 dh cubed, but this is a square. So we have b to the fourth of the outer object minus 1/12 b to the fourth of the inner object. Okay, so you'll have, what is 1/12? The outer is 4 to the fourth minus the inner 3 to the fourth. I don't know what this is. I didn't punch this in beforehand, but 14.58. Okay, this is the area moment inertia for this cross section, right? If you want to assign a coordinate system to this, which is probably best, maybe you have, if we do traditional coordinates, this is the z direction, this is the y direction, and the x direction is the length of the beam, right? The longitudinal length of the beam. Then this is iz in this particular case, which is also the same as iy because we have a square cross section. So important to know what axis you're talking about when it comes to the area moment inertia. But here, this 14.58, that's one error that I see. Here you have 26.83, which I think is something incorrect. So I'm not sure exactly what's going on there. I see that you're trying to do like parallel axis theorem for each individual component, but you don't need that here. And the reason why is even when it comes to doing the shear stress calculation, right here, we're going to have something like tau xy is equal to, you've probably seen it as VQ over IT, but I like to put the subscripts on here. This is VYQZ over IZT. More on this in just a second. But when you're looking at this particular calculation for shear stress, the area moment of inertia of the cross-section is what it is. It's a geometric property of the cross-section. It doesn't matter what point you're looking at, where you're cutting on the cross-section, where you're investigating the shear stress, it does not matter, okay? Area moment of inertia is a geometric property. It's like area. The area of a circle is pi r squared, right? The area moment of inertia circle is pi on 4 r to the fourth, right? It's just a geometric property. It does not depend on where you're investigating the cross section. So we happen to be looking at a particular point that's up here. I think it's called point little a. Doesn't matter. When it comes to area moment inertia, you're looking at the area moment inertia of the cross section as a whole as part of this calculation. So this IZ should be the area moment inertia of the whole cross section, which I think here is 14.58, right? If I've done my quick calculations on my yellow calculator here correctly. Okay, so that's issue number one. This is okay. Here you have your calculation of Q, and I actually think that this looks pretty clean. So I'm okay with what you got going on there. All right. This all looks okay as well, right? So here we're going to calculate VYQZ over IZT. All right, VY, this is your 12 kips, so I like 1,200 pounds, 12,000 pounds. QZ, I think you have calculated this correctly, 6.125. I haven't checked this thoroughly. This is going to be inches cubed. Sorry about my handwriting on this writing pad. It's pretty atrocious. Um, and then your air mode inertia, I think should be 14.58 inches to the fourth here. And then T, which is the thickness of the beam, you're correct to say that it is 1 inch. This is something that can trip people up, especially when you're at this like point A here. You need the thickness of the beam at the point of interest, and so that is 1/2 inch here and 1/2 inch on this side. So you have 1/2 inch here and 1/2 inch here. So the total thickness that's going to give you the maximum shear stress, which is what you're interested in here, is that 2 times 1/2 inch or 1 inch. Okay. Calculate this. I don't know what the number is. I'm too lazy to calculate it right now, but that's the general idea. Okay. That's the first one. That's the easy one. I think that's problem number 2. Let's talk about the one that's a bit more difficult. Actually, way more difficult, um, which is the bolt problem. This problem is hard. If they didn't give you an example problem like this to work through like in class, I mean, you're a sunk ship. Anybody that's doing this without Chegg or without like someone else giving them some private tutoring, they got no chance. So let's pull this in here and let's give a look at it. All right, so I'm going to pull it in and let's talk about it. All right, so here we go. I don't even think I'm going to pull in your work here. It didn't seem like you have all that much work, so let's just go ahead and get into this. This problem is complicated, and it requires a lot of understanding of shear stress in a lot of different ways. So I'm going to have to give you some theory here to help you get through this. All right, so let's envision a beam that is two 1 inch by 1 inch squares glued together. Okay, so let's show it like this. And they're stacked on top of each other. And we got this going on and this going on. And they're glued together right in the middle. So hopefully you can understand what's happening here. I've got a coordinate system that looks like X down the beam, Y up, and we have two beams. This is beam number 1, and it's glued to beam number 2. So if we're looking at this from the side, it just looks like, pretend those are 1 inch by 1 inch. It's not the best drawing. That's probably a little bit better. Okay, these are 1 inch by 1 inch. This is 2 inch total on the top, 1 inch total here on the side. And we have our coordinate system that will be, in this case, y, z. Hopefully you're following all of this. All right. If you have some load that is acting on this beam, let's call this 2p, and you're investigating some cross-section here, I don't know, I'm going to call this nn if you like. It's similar to what you saw in the last problem. Then you're going to have this cut here. Acting on the surface, you're going to have some internal shear, which I'm going to call Vy. Remember our coordinate system here? This is x, y. So you have shear Vy, which in this case is going to be equal to P. If we just have some load 2P there, you can do your shear diagram and understand that that Vy is going to be equal to P. All right? That Vy is going to give rise to a shear stress in this cross-section, which you probably know. That's going to have a distribution that looks like this, right? Maybe you've seen this before, maybe you haven't. But this is your shear, and this is going to be VQ over IT. It goes to 0 at the top and bottom. It's the greatest in the middle. All right? That's nice. But this is missing a lot of additional information that you actually end up needing for the bolt problem that you have. And it's missing these subscripts. And I talked about the subscripts before, but we're going to be a little bit more clear about the subscripts now and here talk about, this is actually tau xy, which is Vy QZ over IZT. I'm guessing that your teacher did not go through the subscripts and the dimensionality of this in such a detailed manner. All right. Let's talk about what these subscripts mean, specifically on the shear stress. So here, this first variable is the face upon which the stress acts. More on this in just a second. The second variable is the direction of the stress. Okay, let's look at this a little bit more carefully then in our little picture. So when I say the face the stress acts upon, this first variable, here, this is a shear on the x face in the y direction, tau xy. So the face the stress acts. What I'm looking at is I'm looking at the normal to the surface which we cut. So here is an axis that protrudes from the normal of the surface. This is the x direction, and this is the normal to the surface. Okay, that's the x direction, right? So this first variable, tau xy, x indicates this is the face that we're acting upon. The second variable, the y, is the direction of the stress. And you can see that the direction of the stress is associated with the force that's acting on the face. So you have this shear load that's coming across the face, Vy, downwards. So the direction of the stress is the direction of the load, which we've labeled here as Vy, because it's a shear in the y direction, Vy. So that's how you get these subscripts on the shear stress, tau xy. It's a shear stress acting on the x face in the y direction. And it's calculated using this formulation, where Qz, this is the first moment of area, first area moment of inertia about z-axis. You've probably learned it as something like y bar prime, a prime. More on that in just a second. Iz, this is the second area moment of inertia. You know this well. T, this is the thickness of the beam at the point of interest. Okay, great. Why does this matter for this bolt problem? Well, it matters for this bolt problem because of the symmetry of shear stress. Hopefully you've learned in your class something that tau xy is equal to tau yx. This is just a general property if you're in static equilibrium that will more or less always be true. And so what this says is that, okay, the shear that acts on the x face in the y direction, which is the shear that you see here, is the same as the shear that acts on the y face in the x direction. Now let's contemplate that and look at that for just a second. What is the y face? What is the x direction, right? So if you think about your two beams that are glued together, and you thought about ungluing them, you would have one beam here and another on top of it. And let's take a close look at this bottom beam. Let's remind ourselves what our coordinate system is. This is the x coordinate system. This is the y coordinate system. So what are you looking at here? Well, there exists shear between these two beams, right? If those beams were not glued together, they would slide against each other, okay? So there's shear inside of that glue that holds it together that must be sort of like counteracting itself at that midplane. And if you think about, well, what's the label that we should label this shear? This is actually shear that acts on the y face in the x direction. So here, this is the y face, right? The normal to the surface. This is normal is the y direction. And this is acting in technically the negative x direction, but you get the point, is that the shear is acting in sort of the negative x direction. Okay, that's the lesson that you need to understand this problem. Now let's look at your problem, okay? Because we needed to understand that to even get into your problem. Let's get into your problem. In your problem, you have a situation where you have these big plates that are bolted to an I-beam, right? I'm going to make a crude sketch here. Looks a bit like this. Okay. And you have these bolts that are coming in here, bolts, right? And it's asking you, right, what's the maximum allowable shearing force that this cross-section can handle before the bolts fail, okay? So what that means is, okay, you've got some shearing force that's coming across the face. We're going to call it Vy. And that you somehow have to relate to the maximum bolt strength that you know is 90 MPa. Yeah, it's not so easy to understand what's happening. So let's look at this from the side. Okay, you got this plate. Got the I-beam. Okay, so this is the plate on top, I-beam. It's got its, big center web. Okay. And then, the plate on the bottom again. All right. Yeah, so this is the thinnest part here right in the middle, right? Okay. So you've got these bolts that are holding this thing together, and they have a certain spacing, right? Let's call the spacing, I don't know, call the spacing phi if you want. Call it whatever. Um, Make that a little more clear. This is phi, the spacing between the bolts, all right? Which is told to you is 125 millimeters, right? It's the longitudinal spacing of these bolts. Now, when I apply a load here, a Vy, what's going to happen is a shear is going to develop inside of this cross section, right? This is your tau x, y. Remember, we have x, y coordinate system here. It's not exactly the shape because the cross section varies, but let's just go with this for now, okay? Tau x, y. But also, what's happening is that there's a shear between the plate on top and your I-beam that is the same, okay? So if we look at this from the top, you have what looks like that big plate on the top, and you have this bolt pattern. Bolt, bolt. And you have the shear force that's sort of the shear that's acting between the top plate and the I-beam, okay? This tau yx that acts between the top plate and the I-beam, right? There's this interplay, this shear back and forth between them, okay? What has to happen is these bolts that exist at every so often, their length every so frequent, they need to cover the shear stress that's generated every so often. So what I mean by that is like this region here is an area. I'm going to call this AY. More on that in just a second. This is an area that these two bolts must protect against. Okay? So this bolt and this bolt, they keep disappearing on me. This bolt and this bolt are responsible for making sure that that section of the beam does not break. Okay? This section of the beam has shear tau yx acting on it. So that means it needs to hold a load, which is, stress is equal to load divided by area. So the load that it must handle or need to handle is tau times A. Or what we're saying is we need to cover an amount of load in this area, which is tau yx times AY, right? Yeah, we're getting kind of in the weeds here, right? Now, how much load um, this tau yx is the same as tau xy, which you would calculate in your cross section, times AY. So this is the load that each aerial section needs to hold to not break. Right? We need to compare that to the failure strength of the failure load of the bolts, right? To understand sort of what load can the bolts hold before they fail, and how does that correspond to what transverse load we can apply before we reach that load that the bolts will fail at, okay? So what I mean by that is let's take a look at the bolts. How much load before one fails? Okay, we're told that the shear strength of the bolts is 90 MPa. And that is a bolt that looks like this. When you have shear that is single shear that looks a bit like this, right? So maybe you learned about this like single shear, double shear at the very beginning of the course. Usually it's taught in the first couple of weeks. But a bolt in single shear like this will have some sort of maximum shear strength associated with it, right? If you look at the cross section of this bolt, right, you're looking at it from above, you got this load coming across. The bolt must resist that load up to some degree, right? We're told that the maximum shear stress that these guys can handle is 90 MPa. So if I know the diameter of the bolt, which it's given in the problem is 18 millimeter diameter bolts, then you can calculate how much load a single bolt can handle before it breaks. So load to failure for a bolt, single bolt here, is going to be its failure stress, 90 MPa, multiplied by its cross-sectional area, which is pi times half the diameter, 9 millimeters squared. All right, whatever that number is. But you can understand how much load is going to take for one bolt to fail in shear. Now, you have pairs of bolts that occur every longitudinal distance. So you actually need to understand like load to failure of the bolts is of a single bolt is 1/2 of the load to failure of one of these aerial sections, right? So, you can hold up to 2 times the load of one bolt because you have two bolts in each of these like aerial sections, right? Okay. So what you need to do is you need to compare. You want to say that, all right, I want to know when I reach a load of 2 times the failure strength of a single bolt. Once I reach that, my beam is going to fail because those individual sections are just going to break, right? This has to be equal to the load that gets generated by the shear stress in the vertical cross section, right? So this has to be equal to tau xy, which you know to be Vyqz over Izt, times area AY, where the area AY is the area associated with each section that needs to be protected by the bolts. This is AY, which I think in your case is going to be, it says 9 by 175 millimeter plates. Okay, so it looks like it's 9 millimeters. Or 175 in width. I don't really understand, but it's 9 millimeters thick, 175 millimeters in width. Okay, this is 175, this dimension. And then this aerial dimension is 125 millimeters. We're told that's the spacing of the bolts. So the half spacing is the same as the full spacing. So AY is 175 millimeters times 125 millimeters. And this is kind of the equation that you need, where 2 times the failure strength of the bolts, this is tau max of the bolts and shear, which is 90 MPa, times the area cross-section of the bolt, which is pi r squared of the bolt, and this is equal to V y q z over IZT times AY, which is, the width, let's call it W, multiplied by the bolt spacing. I don't know if you want to call it S. I think we actually called it phi before. So times W phi. And that's the equation that you need. That's a banger. Told you it wasn't an easy one. Good luck. There's a lot of calculation there. I did that lesson probably about as fast as I could. I didn't mean for this to turn into a lecture, but there's a lot you need to understand to really get through that problem. And it sounds like more than what was covered in your traditional lecture. So Anyway, good luck with it. Happy mechanics of materialsing.